Good morning, good afternoon, good evening, good night, depending upon where you are. Welcome to Association of North America Higher Education International's webinar, Partially Square Structural Equation Modeling, Recent Advances in Model Assessment with Professor Dr. Marko Sarstedt. My name is Professor Cihan Çobanoğlu. I am the McKibben Endowed Chair Professor at the University of South Florida, Sarasota, Manatee. And I also serve as the president of Association of North America Higher Education International. As you all know, we've been bringing you interesting webinars, but this particular webinar has been one of the most popular ones, which we are very, very happy to receive a lot of interest in this particular topic. I would like to first welcome you to this webinar and introduce Dr. Faizan Ali. He is the assistant professor at the University of South Florida, Sarasota Manatee's College of Hospitality and Tourism Leadership. Also, he serves as the director of research methods and statistics for ANAHEI, the organization. I would like to thank Faizan for his very hard work and very, very useful webinars that he is organizing. And I would like to turn the webinar to Dr. Ali. Dr. Ali?
Thank you, Dr. Jihan. Thank you. And once again, I would like to thank Marko for accepting our request and doing this webinar. Again, we are all a bit overwhelmed with the number of people who registered to attend the webinar. And that's why we were late for a couple of minutes. And for that, we really apologize. Okay, so Marko, well, again, I don't want to talk too much about Marko, but he is the real deal these days. And he is doing quite a lot of stuff in statistics. His main area of research is basically marketing, but he is also working in statistics, and he is these days one of the top researchers in partially squares-based structural equation modeling. Marko has extensively published in top-tier journals, including the Journal of Marketing Research, Academy of Marketing Science, Tourism Management, Long Range Planning, Journal of World Business, and Journal of Business Research. He recently received 4 or 5 awards from Emerald, which is, I think, a record in itself, because normally people get it once or twice in their whole career. So Marko is doing amazing things, and he's going to talk about some of those things in his webinar. With that, before we start the webinar, I also want to go through the housekeeping stuff a quick. Those of you who are watching the webinar through Zoom, and I see that there are 106 people on Zoom right now, in addition to the people on Facebook Live. So for people who are on Zoom, if you see, there would be an option of raise hand. And if you can just click on that, that would give us an indication of you are listening to us properly and there's no breakup in the voice or anything. Now, when do you use this raise hand is where you have a question, you can just click on raise hand and ask your question. We'll try to get the answers for your questions. Just a quick thing, if you can just click on raise hand, that would make us feel that you are also listening to us and you understand how to do the raise hand. All right. Okay, other than that, we have ANAHEI, and now we do talk about what ANAHEI is in the start of every webinar. So basically, it's a non-profit organization, and the main intention is to promote and encourage a global culture. We do have quite a few member institutions, and most of these institutions work on globalizing student and faculty successes and do different type of initiatives in order to deepen global engagement, such as this webinar or some other things. Some of the stuff we do is encourage people to take part in research in 3 minutes program, which is summarizing your research in 3 minutes. There's a visiting scholars program ANAHEI is hosting, and then there are a couple of journals like IIBA Journal and Journal of Global Education and Research. In addition to that, there's a conference, which is Globe Conference. It's coming up June 4 to 8 in Sarasota, Bradenton. I would really request you, if you want to have a beautiful, an amazing conference in a beautiful location, to consider coming to this conference. For other details, you can always go to anahei.org and look at all the stuff, amazing stuff ANAHEI is doing. The next upcoming webinar we'll have is on May 2nd, and it's about how to use guest data to increase direct booking. So you can mark your calendars for that webinar. All these webinars we have done, the previous ones and the upcoming ones, they are already on the website. The ones which already been conducted, the recordings are also available on website. So if you want to share them with your colleagues or with your students, you can always go to the website and get those webinars. With that, I'm done with the introduction, and I would hand over the mic to Marko to start his presentation. Marko?
Yeah. Okay. Hold on. There we are. Okay, does it work now?
Yes, we can see your screen and it's all good.
Yeah, super. So, hi everyone. First of all, welcome from hopefully all over the world to this webinar. Very excited to be here. Also, thanks to ANAHEI, Faizan, fantastic. Thanks for having me. And it's a great honor and a great pleasure to talk a bit about recent advances in model assessment in PLS. Well, Faizan already did a nice job in introducing me, so I'm not going to be talking about myself too much. It's probably not of interest anyway, but actually PLS is not my only area of research. I also work in data quality measurements topics, especially, which works pretty well, obviously, with PLS. But looking at these Greek symbols and formulas is sometimes a bit depressing. So I also work in consumer behavior, specifically in context effect research and sensory marketing topics. So if you ever want to discuss some of these topics with me, I'm happy to do so. But well, today we talk a bit about different things in life, namely PLS. And as you might have heard, we published quite a bit on PLS, not only journal articles, but also a series of books. Well, here you see our recent, basics book, introductory book, Introduction to Partially Square Structure Equation Modeling, co-authored with Joe Hare, Thomas Halt, and Christian Ringler. And well, we had quite a few colleagues who said very nice words about this book, and it's well received in the market. Thanks to you, everyone who's regularly reading it. Thanks for supporting us. It's great. It's also great that this book has been translated into several languages here. There's a Spanish version actually coming up. There's already 2 Chinese versions and a Persian version. That's pretty remarkable for us, and it's just a small indication how well PLS has really developed in the last couple of years, and that is now an established method in the market. We were kind of surprised how well these books were received, and we started planning an advanced book pretty soon after the launch of the primer. And this is out now, Advanced Issues in Partially Square Structure Equation Modeling, that was actually published mid last year. Some of the topics we're going to be talking about today are actually documented in here, but not all of them, because recent advances really means recent advances. So I'm going to be talking about things we are actually working on at the moment and that are coming up on the horizon, really. And some of the topics have just recently been, resolved, I would say. Yeah. Okay, as most of you will know, and Faizan already mentioned it, PLS has really undergone a rapid development in the last couple of years. It's just an overview of the number of PLS studies in the major journals in marketing management and in MIS Quarterly, which is kind of probably the flagship journal of the discipline. And you see that the number of PLS studies is really increasing constantly, and this is also my impression when I look at the citations, the number of emails that we get. It's really a method that has established itself in the market and is used by many disciplines, not only business research, but increasingly in other fields like engineering, medicine, actually psychology, and so on. So we actually just did a little analysis of some other fields, and we were surprised to see how strongly it is now disseminating into other fields of science, which is obviously a good thing. Yeah. But with all these things, obviously also some discussions emerge. Under which circumstances should we use PLS? Is it actually a structural equation modeling method? What are its limitations? and strength, and that's actually a good discussion. I think we learned quite a bit during the last years, and well, I'm always encouraging all of you also to look critically at this method and any method. There's no silver bullets out there. Neither method in the world can resolve all issues, but we are just learning about, well, the mechanisms that underlie PLS, at least to some degree. We already learned quite a bit, but we are still working on it. But anyway, just a quick recap of some of the concepts we're going to be talking about. I just assume that not all of you are like hardcore users of PLS and structure equation modeling. So first, to get started really easily, just some terminology. What you see here is a path model. That's actually the path model I'm going to be working with in this webinar. This path model is also the one that we use in our books and also in some of our publications as to showcase PLS and how to run analysis. What you see here, these bubbles or ellipses, these are actually latent variables or constructs. So entities that cannot be measured directly or observed directly. That's what makes them latent, kind of. And we have the measured indicators here, the yellow boxes. These relate to, for example, items in the questionnaire. They can also relate to variables derived from secondary data, such as, I mean, Facebook data, whatever, some internal or external secondary data, wherever that comes from, such as CRM systems, for example. So what you see here is actually a model of corporate reputation. You might be wondering now, well, there's nothing like reputation in here. That's actually true, but we conceptualize reputation in a two-dimensional way, meaning that there's an emotional and a cognitive component. So you can kind of like a company, but you can also think it's pretty incompetent. And the other case could also be that you think a company is very competent, but you just don't like it that much. Yeah. So these are the two dimensions of corporate reputation: likability and competence. This model is also about learning about the antecedents of reputation. These have been identified in prior research works, and you can see here several of these, such as CSR, which stands for corporate social responsibility, attractiveness of the company, quality, performance. So these are the antecedents of reputation, of the two reputational dimensions. We're also looking at the consequences of reputation, more specifically about on customer satisfaction, customer loyalty. Two things that you will notice here. First off, the measures, sometimes you see arrows pointing from the indicators to the constructs. That's what we, like from a measurement perspective, refer to as a formative measurement model. So I'm talking about the measurement perspective here now. And the other direction is here. For example, for likability, you can see that there are three indicators where the arrows point from the construct to the indicators. And this is the so-called reflective measurement model. This is the first thing that I want to point your attention to. The other is the single item construct. Customer satisfaction is measured with a single item. The ones that have maybe read some of my research will know that I'm not a particular fan of single item constructs. I would also advise you not to use them. They are primarily practical, that's true, but they also deflate the model estimates, meaning that the path coefficients that go out and go into such a single item constructs are likely going to be too low, meaning that the corresponding paths are not going to be significant. And this is not because there's no effect, but it's simply because your measurement model is not of sufficient quality. Yeah, so there are instances where this works pretty well, but in this case, we included it only as a showcase so that users understand how to validate these single item constructs. So that's the model we're going to be working with. And here's some terminology just in case you need to flip back during the webinar. We're going to be talking about some of these things here, such as reflective and formative models. Well, depending on which model we are looking at, we primarily look at the loadings, which are simply bivariate correlations between the construct and the indicator. and the weights are partial correlations. Yeah, also correlations, but they mean, well, how much is a certain indicator correlated with the construct, given that there are also other indicators that also have a significant bearing on that construct. We see the structure model here. The structure model defines the relationships between the constructs. They are indicated as errors here, so these are actually predictive relationships, and we have the estimates for these errors are the path coefficients. Yeah? And each of these latent variables or constructs has an own measurement model, yeah, such as here, y1, this is the measurement model for the latent variable y1, and y1 is exogenous here because it predicts y3, and y3 is endogenous because it is being predicted by y1 and y2. So just some recap on the basic terminology here. So we are actually, today we are dealing with a very specific part of PLS modeling. We established such a 6 or 7-step process, depends on how you see it. We typically start with the specification of the structure model, followed by the measurement models. We collect the data, get rid of outliers, straight lining, all these things that are common in statistical analysis. We estimate the path model, and then we engage in the measurement model assessment. This is fundamental because if the measures are not of sufficient reliability and validity, it makes no sense to look at the structure model, that is the results or the estimates between the constructs. It's obviously, if you have garbage in, meaning that the measures are not of high quality, then there's garbage out. Whatever comes out of these measures is not really meaningful either. Yeah, that's why we first need to look into the measurement model qualities. The measurement models, we're not going to be dealing with this today. There's ample literature on measurement model assessments. I just want to point your attention to some recent advances here in reflective measurement model evaluation. The HTMT, heterotrait, monotrait, ratio of correlations, that's a new measure, relatively new measure for assessing the discriminant validity of reflectively specified constructs. We have an article together, like Christian, your Kensler, and myself in JAMS, published in 2015, and we have a recent follow-up article, George Franke and myself, in Internet Research. In case you're interested, I'm happy to send that to you. It's also available on ResearchGate. And with Faizan, actually, we have a recent study on formative measurement model assessment and redundancy analysis here. Please check our reference list. I'm happy to send that to you. But anyway, today we're going to be talking about the structure model assessment. And structure model assessment basically deals with 4 steps. First, we need to check collinearity within the structure model. And this is usually taken care of by discriminant validity assessment. So if your constructs are discriminant valid, they typically also do not have significant levels of collinearity. The second thing we look at is actually the significance and the relevance of the structure model relationships, the path coefficients. And this is done via bootstrapping. So I'm not going to be talking about step 1 and step 2 now, because these are pretty well established. It's getting actually more interesting here with step 3 and step 4. And let's focus on these now. So looking at step 3, the predictive performance of a model. Well, there are actually 2 types of predictive performance we can look into. There's the in-sample prediction, and there's the out-of-sample prediction. In our early works, we didn't really differentiate between these 2, and this contributed to some confusion. Now in our latest works on PLS and tutorial articles, we clearly distinguish these 2 concepts. So in-sample prediction means that you actually use the entire data set to estimate the model, and then you use these estimates to predict observations from the same data set. Yeah, it's kind of well, using all the information that you have, and then you try to reproduce this information. It's commonly, this is what the coefficient of determination does, the R-square, and it's actually considered either as a measure of explanatory power or in-sample prediction. Yeah, it's very much the same. Yeah, so we're going to be talking really briefly about this one. There's also the effect side F-square, which we're not going to be talking about today. The problem with the R-square is that it's only related to the in-sample, so to the data that's already lying around. It says nothing about a model's ability to predict new observations. But the thing is, this is actually what prediction is all about. Yeah, you want to know how a certain or what a certain observation looks like for which you don't have the entire information. Yeah, so you want to predict new observations, kind of the analogy of a bank where you want to set up some credit rating system and you want to assign credit scores to your customers. And you do this using your entire database, and then a new customer comes into your bank and you want to have, well, a reasonable good prediction of what the credit score for this new customer is going to be based on, for example, socio-demographic information. And that's the same logic here. We actually, in an out-of-sample prediction case, we want to predict new observations or observations that have been gathered in a different context. The blindfolding-based Qsquare is kind of a measure of out-of-sample prediction, but for reasons that I'm going to be talking about, it's actually not truly an out-of-sample prediction method. Much better here is so-called PLS-Predict, which was introduced 1.5 years ago by Galich Noeli and some colleagues in Journal of Business Research. And I'm going to be talking about this procedure and guide you through well, how to use it actually. So I'm sure all of you will be familiar with the R-square. Coefficient of determination tells us how much variance of a certain endogenous construct is being explained by its direct antecedents. Varies between 0 and 1, and there are also rules of thumb that we define in our book. Well, actually now the webinar is given by the only author who opposed having these rules of thumb in the book, because I just don't think that they are very accurate. Reason is that it depends obviously on the model and on the context. Let me give you an example. If you're in a consumer behavior context and you run a certain experiment in the lab, and in this experiment you control like all the extraneous factors, so all influencing factors are controlled for, you want to be able, really be able at the end to explain a certain behavior. So the R-square, you expect it to be pretty high, like 80%, maybe 70%, something like this. However, if you run a study and you want to explain abnormal stock returns, so you want to know why people purchase stocks, or you want to explain why stocks move in a certain way they do, to be more precise, where having an R-square of 80% would be marvelous. In fact, if I came up with a model like that, the last thing is that I would do is publishing this, because I would have found like the formula for predicting stock returns. And then I would just keep that to myself and already think about which deserted island I'll emigrate to. Yeah, so it depends on the context. We have these rules of thumb in the book, but I would be a bit cautious. I would advise you to just look into prior research, compare your model with that of prior researchers, also in terms of model complexity, because the R-square obviously typically increases with more predictors, yeah, like practically always. So that's what I would advise you to do. There's also the adjusted R-square, which we use for model comparisons. However, latest research I'm going to be talking about at the end of the seminar tells us that the adjusted R-square is actually not a very good indication for comparing models. So I'm just going to skip this part. Yeah. A bit more interesting is the blindfolding or blindfolding-based Qsquare. And blindfolding is actually a procedure in which we systematically omit certain data points. Then we replace these data points with a naive prediction, which is a mean. And then we use the estimates to predict these data points. So this kind of sounds like out-of-sample prediction, right? But actually it isn't, because we don't eliminate entire observations, but only specific data points. let me show you an example for this. Yeah, I think it gets a bit clearer when you actually see a model and see how that works. So what you see here is a simple model. We've got two exogenous constructs, y1 and y2, and an endogenous construct, y3. So the measurement models here are not relevant for us now. The endogenous needs to be measured with reflective indicators, which is obviously the case here. And we have a small example data set down here, just 7 observations. Yeah, and these are standardized indicator scores. So these are not the original scores, but they are the ones after standardization. And as you can see here, we have got these 7 observations for x1, x31, x32, and x33. So what we are doing now, we are defining an emission distance. And this emission distance tells us which of these data points are going to be emitted in each of the blindfolding runs. So for example, if we specify an emission distance of 3, that means that every 3rd data point is emitted in each blindfolding run. And this is actually indicated here. For example, in the first run, all the data points where this little label D1, the blue one, is put, these are actually emitted. Yeah, so the first observation of x31, the 4th observation of x31, and so on. So we are moving here by column and from left to right. In the second run, all data points with D2 are going to be emitted. And in the third run, all the ones where we have the D3 label are going to be emitted. So that's actually, this is actually illustrating it. And in the first blindfolding run, well, we still have data for all the observations in place. The boxes that are now shaded here, for these we have the mean value replacement. And the model is estimated for blindfolding run 1, 2, and 3. And in each of these runs, we try to predict the emitted data points. And I'm always talking about data points, not observations here, yeah? Because again, we're not deleting entire observations. Depending on which of these methods you choose, there are different ways of actually predicting the dependent constructs indicator points. There's the cross-validated redundancy and the cross-validated commonality. They just take different routes for prediction. Usually they don't diverge very much. And well, there's a slight tendency to use this cross-validated redundancy because, well, we have always done it that way. But there's not strong reason to prefer one over the other. Win Chin once said, the cross-validated redundancy fits PLS like hand and glove. And so that's kind of why it's probably established. I don't know. Yeah. So we also recommend using it. But as I said, there's not much difference anyway. Generally, we say, well, Qsquare should be larger than 0. Then there's some type of predictive relevance. And we can also relate to these rules of thumb here, what constitutes strong Qsquare and not so strong Qsquare. But generally, Qsquare should be larger than 0. Then there's some type of prediction action going on, or predictive accuracy in the model. The only thing you need to consider is that the emission distance D must not chosen such that if you divide the number of observations by D, that you actually get an integer value that has got something to do with the replacement or with the omission of the data points. Yeah. For example, if you have 100 observations, D must not be 2, 5, or 10. Yeah, you could choose D as 7, for example. So we, at some publication, I think we erroneously, and I think that's really erroneously, we refer to Qsquare as a measure of out-of-sample prediction. And actually, strictly speaking, it's not. It's kind of like an out-of-sample prediction method, but not really, because you're not omitting entire observations. This has been critically noted by Galich-Mueli and her co-authors in the JBR paper. And we looked into the machine learning literature, and that's actually truly correct. And machine learning is kind of the blueprint literature for prediction, in our opinion. So that's why we corrected our statements in that regard. And we're a bit cautious here in labeling it in-sample or out-of-sample prediction metric. Yeah? So where it gets more interesting now, and that's probably in the stuff that most of you will be interested in, is actually PLS-Predict. because PLSpredict is truly a method for out-of-sample prediction. In PLSpredict, what we do, we actually omit certain part of the observations. We estimate the model, and then we try to predict the omitted part. So what PLSpredict does is it uses a training data set. So training data is the data that is actually being used for model estimation, and the testing data or holdout data, which is actually not used to estimate the model. That's the one that we actually want to predict at the end. When we talk about prediction, we have to talk about errors. Yeah, what's the error in a prediction? Yeah, so for example, you would have an original value of 5, and you're predicting a 6. Well, there's an error, right? So your prediction is too high. Yeah, it's 6, and the original value is 5. So there are different ways how to express such a prediction error. Well, a very naive way of doing that is just to take the error as the predicted value minus the test value. So this is a very naive way of putting it. The problem obviously is that positive and negative deviations could cancel each other out. So let's say once you have a prediction error of 1 and then of -1, on average you would be fine, which is obviously not very sensible. That's why there are different metrics here, and probably the most popular one is the root mean squared error of predictions. So as you can see here, it takes the prediction error and minus the average prediction error and squares these differences. And this means that smaller deviations, like smaller prediction errors, are not considered very severe, versus very large prediction errors are actually considered as very severe. So they actually are weighted stronger because of the squaring. So the RMSE is typically used in prediction studies, probably because it weighs greater prediction errors more strongly than smaller errors. However, there's also the mean absolute error, which also features strongly or prominently in research. So this is just the absolute value of the error and then divided by the number of observations. And we have the MAPE, the mean absolute percentage error, which I think in the 90s was kind of preferred, I think. But it has several characteristics which make it not really, well, very attractive, particularly not for PLS. Because as you can see here, it is not defined for variables where there's a 0 value. As you can have in the denominator here, the x test, and so if this is 0, you're dividing by 0, which is obviously not working. Yeah? So this is particularly problematic in PLS if you use the MAPE for latent variable scores, which usually oscillate around 0, and it could be that because of rounding, you actually have a 0 value here, and then, well, the entire analysis collapses. Another issue is that equal errors above the observed value result in a greater absolute percentage error than those below. So actually, various errors above are weighted more strongly than errors below in MAPE. That's why we don't advocate using MAPE, but focusing on the MAE or the RMSE. Use the RMSE if you believe that stronger deviations, like higher prediction errors, are more severe. Use MAE if you think, well, there's not much difference. If it's a small or big error, it doesn't matter. All of them are weighted equally. Finally, we have the Qsquare. And this is actually analogous to what we've just seen in blindfolding-based Qsquare. I'm going to be talking about that when we see some examples. We actually use this as a kind of a naive benchmark. What does that mean? We actually just use the training data's mean as a prediction for the omitted variables. So we just use the training data, take the mean value, and this is kind of our best guess. This is the most naive benchmark that you can think of. Yeah? So if a model performs badly in terms of Qsquare, you really have a problem. That's how we can put it. So how does PLSpredict really work? I told you that we split the data set into a training and a holdout set. And how does that work? We first need to specify K. K is the number of folds. This tells us into how many parts the data set is being split. So we estimate the model k times, meaning if you set the folds to 5, you're estimating the model 5 times, but not with 5 parts of the data set, but only with 4. One is being omitted in each of the runs. We predict the observations using the estimated model parameters and calculate the prediction statistics based on the holdout set. The thing here is that, well, as this is a random process, the partitioning into k equal parts, it could be that in one of these samples, you actually have a very extreme sampling. Yeah? So it could be that some of the observations or some of the extreme observations are put into one of those folds. That's why we repeat this procedure R times. R is the number of repetitions. Well, which values to choose for K and R? Well, a bit difficult to tell. In prediction literature, people usually use 10 folds and 10 repetitions. So to get some stability of the estimates. So this is just illustrating how that works. For example, here in the first fold, we have our training data set. So we have these 4 buckets of data. These are actually used for running the model. And whatever we get out of here, the estimates are used to predict the test fold, the first one here. And we are estimating the prediction statistics over here to the right-hand side. Next, we use the second set of data. We take this out and use this as a holdout data set and use the remaining data sets, the remaining folds, to predict the holdout set. And this just repeats until we have taken out all the holdout data sets and all the folds possible. All these test values here. And we repeat this thing 10 times. So we get different partitions in the test and training data set. So the problem with this is, generally, we don't have any standard of comparison. Like RMSE and the MAE values, well, they don't tell us very much as such because they depend on the scaling of the variables. So we need some type of standard of comparison. And there are actually 2 different standard of comparisons or benchmarks that we propose. One is the naive benchmark, the super naive benchmark, let's put it like that, the mean value Qsquare. This just uses the mean value of the training sample. This is the naive benchmark. We want to predict better than that. Another thing that we can do is specifying a linear model. And this linear model takes the exogenous constructs indicators and uses these as independent variables in the regression. And the dependent variables in the regression are the indicators that we want to predict. So I'm just flipping back really quick and show what that looks like in our data set here, or in our model here. So for example, if we want to predict the 3 indicators for customer loyalty, decide, gain, remain customer, and recommendation, we would run a regression of these 3 indicators on these indicators here of CSR, attractiveness, quality, and performance. So all these indicators here of these 4 exogenous constructs would be used as independent variables. So why is this useful? Well, it gives the algorithm some indication what is exogenous and what is endogenous here. But the entire model structure is omitted. So we don't have any information, or we don't process information regarding the PLS path model structure. So we don't know that there's likability and competence in between and what these relationships look like here. That's all omitted. That's what makes this a naive benchmark. And we compare now the RMSE and MAE values of the PLS model with naive benchmarks, and we would expect that we get lower prediction errors, like lower RMSE and MAE values for the PLS model compared to the naive benchmark, because at the end you want your model, which has this nice structure that you came up with in your theory, to predict better than the most naive thing that you can think of. So if we still have time, I can show you the results for doing this actually in the Smart PLS software. But in light of the time, I just want to move on and talk a tiny bit about Goodnessoffit, because I know that this is a topic that several of you are probably struggling with. So there's actually need for Goodnessoffit measures in structural equation modeling. Yeah, because you want to be able to tell whether you have a good model or a bad model, right? I mean, this is kind of what structural equation modeling, at least partly, is all about. And there's a strong tradition, obviously, in covariance-based structural equation modeling to look into fit measures. So it's actually like an automatic kind of, you first look into the goodness of fit measures, and if the model does not fit well, you kind of modify it, which is, well, you're actually leaving the confirmatory route and going into exploration, which is actually not what you're supposed to do, but that's kind of research reality. Yeah, strictly speaking, if the model does not fit well, you would have to, well, reject it and start all over again, which actually not one really does. So we are kind of exploring different model alternatives. And all these different fit measures in the covariance-based context are based on the same logic, namely that you have a correlation matrix which you can observe, the empirical correlation matrix, and the one that is model implied. Model implied means that it is kind of a reproduced correlation given that the certain model that you have. So, and the model estimates that you have. So here you're reproducing the correlation based on the model estimates. And well, if the model fits very well, fits data very well, you would expect that there's a small divergence between what you actually observe and what you reproduce based on your data and the model that you specified. Yeah, so this difference should be minimized. And this is what practically all measures of model fit in covariance-based SEM are all about. Yeah, they somehow quantify this divergence between the empirical correlation matrix and the model implied correlation matrix. And they are basically based on the Qsquare test, which tries to quantify this difference, right? And there's also something like goodness of fit, obviously, in PLS. It started actually earlier than 2005, where Tannhaus and colleagues proposed the goodness of fit index. And it's actually a nice index, but it's kind of mislabeled because they said, well, it's an operational solution to the problem of the fit measure in PLS, and actually it is not, because it follows the PLS tradition in terms of, well, prediction, but it's not goodness of fit as we would ever define it in a covariance-based SEM sense. So you see, in the original publication, it looks really fancy, but it's in the actual computation, it's really easy. It's just the average commonality times the average R-square and the square root of this. And the logic behind this is that you want to explain as much variance as possible in the model, the R-square, and also in the measurement models, that's a commonality. The problem with the goodness of fit index is that it makes very little sense to use it for single item constructs because the commonality, or the average variance extracted, same thing, yeah, is by definition 1. So it makes little sense. It's not defined for formatively measured constructs and doesn't really consider model complexity because you can simply boost the R-square by just adding more errors pointing at a certain construct. So you can, if you make the model more complex, you increase the R-square by definition, yeah, unless the exogenous constructs are all perfectly uncorrelated with each other and with the dependent variable, which is actually never happening. You know? We also took a look at its performance in our study here in computational statistics. And I'm not going to be talking about that. I just put it in case you're interested in learning more about this and how it actually performs. But the bottom line of the study is that the goodness of fit index is actually not capable of separating like good models or the true model from wrong models. Yeah, and it's actually not even indicating acceptable models like parsimonious models compared to other grossly misspecified models. Yeah, so that's why we don't really advocate it, but it has its uses in other contexts, but it's not a goodness of fit index. You know? But there are actually goodness of fit indices out there for PLS, and they actually have been proposed in the 80s. Lohmöller, who was a doctoral researcher together with Herman Woltz, who initiated PLS, he came up with several measures and he borrowed them from the covariance-based SEM world. So there are basically 3 types of goodness of fit measures. The first one follows the exact same logic as the ones that I just talked about in CB SEM sense, in the covariance-based SEM sense. They try to quantify the divergence between the correlation matrix that you actually observe and the one that is implied by the model. So one is the SRMR, and this is nothing but the standardized difference between the observed and kind of the predicted or model implied correlations. And this measure is scaled such that you would actually like to have values close to 0. The threshold value that you frequently read is like 0.08 or 0.1, depending on which paper you're looking at. There are also other ways to quantify these differences via distance measures. We're going to be talking about these, the ULS and DG. They're just two different ways how to quantify these distances. The second type is the RMS theta, the root mean squared residual covariance. And the root here to indicating model specification issues is a bit different. What you do here is you look into the residuals of the measurement models, of the reflective measures. You're looking at the residuals. And these residuals should not be highly correlated, because if they do, it suggests that there's some common error that yields or triggers these correlations between what you cannot explain in the model, between the residuals. So there must be, for example, something missing, or there is some model specifications is wrong. So these outer model residuals, or this measurement model residuals, should not correlate highly. Hence, the RMS theta should be really low, which means like between 0.12 and 1.4 and lower than that. Finally, there is the NFI, which has also been suggested in a PLS context. But, well, just to give you an idea, it compares the chi-square value of the model that you're looking at with that of a null model. Null model means it's a naive model with actually no information, just the constructs, no linkages. And this has actually been debunked in a CB-SEM context. It's been very ineffective. And well, I'm kind of struggling with this measure also. So I'm not really going to be talking about this today, but like more about these type 1 and type 2 ones. If you want to use them, then rather rely on the SRMR, exact model fit test, or RMS theta. So one problem here is we have the observed correlations. Okay, these are clear. That's the one. These are the ones that we can actually get from our indicated data. But what are the model implied correlations? Where do they actually come from? And well, there are two ways of doing or looking at that. And the thing is, this is not really resolved. So where do the model implied correlations come from? So if you look at the recent PLS literature, there are like new guidelines for using PLS, and they strongly advocate using Goodnessoffit measures. This is fine, but the thing is, they remain silent on how these measures are actually computed. So how the model implied correlations are actually, where they are coming from, and even software that actually gives you indication of the SRMR, for example, gives no technical documentation on where these model implied correlations actually come from. And this is far from trivial, because there are like different ways of computing them. And here are just two ways that are actually implemented in Smart PLS. One is the so-called separated model. And here, the model implied correlations are derived from the construct correlations. So for example, you would have the correlation between 1y and y3. You would use this. And based on these correlations, you can derive the model implied indicator correlations. The other way of doing it, for example, looking at the actual model estimates. And here we would use the correlations between the constructs. If they are actually not linked in the model, like y1 and y2, we would use this correlation between these two constructs. And another way, if they are actually being linked, we use the path coefficients. So for example, y1 and y3, you can see an error pointing from y1 to y3. Here we would not use the bivariate correlation, but the path coefficient, which, well, gives you also the correlation, but considering the fact that there's also y2 predicting it. So the partial correlation here. What about the linkage between y1 and y4? Well, here we would take the total effect. You can see that you can go from y1 to y3 and from y3 to y4. And if you multiply these path coefficients here, you get the total effect. And this is then being used as input to derive later on actually the model implied correlations between the indicators. So these are just two ways of getting the model implied correlations. And well, for the SRMR, you would expect the SRMR to have an absolute value less than 0.08 or 0.10, depending on which literature you look at. You can also look at it from an inference statistic point of view. You can compute the confidence interval and check whether the original value of SRMR falls into, let's say, the 99% confidence interval. What does that mean? If it falls into the confidence interval, well, you can be sure that the estimate is actually reasonably stable. If it falls outside, well, it's unstable. Then you would tend to reject the model. So this sounds pretty logical, but there are some issues here. So first off, we don't really know about the threshold. So there's no full-blown study out there, simulation study, which actually looks into the performance of the SRMR. So we don't know how it's actually performing. Well, we have got some idea, yeah. We actually did it in an organizational research methods article, but we don't really truly know how it performs different model constellations. Thus, the rule of thumb is tentative. Yeah, we kind of derived this and from the CBSEM literature and also from our simulation study, but that was really small scale, so we don't really know. Plus, it's unclear what the model implied correlation matrix should look like. Is it the saturated or the estimated model or some other way? So we don't really know that either. A similar situation emerges here for the distance measures. So this is like in a cluster analysis where you have data and you compute distances. You can compute the distance between two data points. Same thing here. We want to compute the distance between the empirical correlation matrix and the model implied correlation matrix. And there's like a almost infinite number of distance measures that you can use. Your Chancellor and Theo Dijkstra, they proposed a geodesic distance and unweighted least squares distances. Well, because prior researchers used related measures, but they could have also used other measures. Yeah. So the issue with DOLS and DG is that the absolute values don't tell you anything because they depend on the scaling of the data. So we have to look into the inference statistics. And same thing here, we check whether the original value falls into the 99% confidence interval. If it does, it's fine. If not, we would have to reject the model. So same thing here. We don't have really large-scale simulation evidence of these criteria's performances. We don't have clear guidance whether to use geodesic or the unweighted least squares discrepancy. And same thing as before, what does a model implied correlation matrix look like? Finally, the RMS theta, I'm pretty much in favor of this metric because it's kind of nice, like from a theoretical point of view. It's convincing, I think. If there are strong residual correlations, there's something wrong in the model, it's a misspecification. So this kind of makes sense. But it's only really defined for reflectively specified models. Actually, Smart PLS also gives you the RMS theta for formatively specified models, but this is based on the loadings that you can also compute in the formative specification. So this is really not really reasonable. Yeah, so it actually is only reasonable to be interpreted for reflective models. But same thing here. Rule of thumb is tentative. It hasn't really been evaluated full scale. So I'm skipping the NFI. I wouldn't advocate it, but from my prior descriptions, you can already see that I'm a bit skeptical regarding the use of these Goodnessoffit measures. It's not that I don't appreciate the value of using Goodnessoffit measures. It's just we know very little about their performance to date. Yeah, and I'm sure that there are researchers out there, maybe you're listening now to me, and who are running simulation studies to see how they actually perform. And that's what we actually need. Yeah, so there's strong need for simulation studies like this. But there's a second reason why I'm a bit skeptical about the need for Goodnessoffit. And there's probably a need, but I wouldn't overemphasize it. Yeah. Reason is that PLS has actually been designed as a causal predictive method. So what you want to have is a model which fits the data well, and not like perfectly, but well, but also does a reasonable good job in predicting the dependent variables. if we now strongly advocate the use of Goodnessoffit indices, we go the same route as CBSEM, where fit is everything. Yeah, so we start tweaking around with the models until they fit. Yeah, until like squeeze the data in the model until they confess. And I'm not a big fan of that because I think it puts a hold on our creativity in research. But I also see the upside of using Goodnessoffit, obviously, because you don't want to have a grossly misspecified model. So I truly think that we need some kind of balance between having a good model that is correct in a, well, Qsquare sense, yeah, but it also should predict well. And these are two extremes, explanation and prediction, which we have to somehow merge to a certain degree. And that's not easy, yeah. There's a parental affection in social sciences for explanation. So we just love to look into model fits. We love to look into these things, but it's a kind of ironic because at the end of the day, what we want to do is give managerial implications. So we want to give recommendations to researchers. And you look at those papers and they always talk about model fit. And you look into all these fancy statistics in CBSEM, and then you have a well-fitting model. But at the same time, well, CBSEM is grossly unsuited for prediction. That's the first issue. And then at the same time, well, a model that fits well is not necessarily a good predictive model. It's actually quite the opposite usually. Yeah? So a model can be very well in terms of fit, but it predicts very badly. And similarly, a grossly misspecified model can be perfect in prediction. Yeah? If you look at this text down here, and I just copy-pasted it into here and highlighted some things. You might have read it by now. This is actually a recent article by Hoffman and colleagues on prediction in social systems in science. And they criticize our parental affection for explanation. And it's actually true. Yeah, I fully concur with this. So that's why I'm a bit skeptical about Goodnessoffit, the concept of Goodnessoffit in PLS, but I still see the value. So I don't want to debunk it as being useless or so, not at all. Yeah. But we should be cautious in balancing explanation and prediction. And that's actually what we try to communicate in our latest research articles. Finally, to wrap it up, we have been working during the last couple of years on model selection issues. And this also relates to structural model assessment somehow. So there are situations where you have different models stemming from competing theories. Yeah, so you might have theory A, which suggests a certain model structure versus theory B, which suggests a different model structure. So which one are you going to use? Yeah, model A or model B? And up to date, or up to certain weeks ago, really, people would be looking into the adjusted R-square. Yeah, so the adjusted R-square gives us an indication of the explanatory power of a model, considering also the model complexity. So it penalizes a complex model. The thing with this is it doesn't really work well. And we actually showed this in a recent paper. And in this paper, we also give recommendations of criteria which you can use for model comparisons. These will look familiar to you because they are actually part of every statistical package that runs regressions or also factor analysis. These are called information criteria, and they have been developed in the information theory context. They are typically formulated in terms of the log likelihood. And as you might wonder now, well, PLS is a non-parametric method, so where does the likelihood come from? Well, there's no need to really, because they can also be written in terms of the sum of squares error. And that's actually when you run Stata, for example, or most R packages, that's how these criteria are actually computed by these packages. So they don't run like likelihood or maximum likelihood in the background. They actually use the simple OLS, ordinary least squares, and use the sum of squared errors to compute these criteria. The only issue is we need to have normally distributed residuals, which is, however, practically always the case. Yeah. So even if they're not normally distributed, these criteria are pretty stable. So in our forthcoming Journal of the Association for Information Systems paper, we actually look into the performance of these measures for model selection, meaning can these measures identify wrong models and can they identify the true models or at least parsimonious versions of it. And the BIC, the Bayesian Information Criterion, and the GM, they are particularly well suited for these purposes. We also have a follow-up paper in which we actually look into the predictive performance of these criteria. So do these criteria choose a model that fits well, but at the same time does a good job in terms of prediction? So which of these models that we're looking at actually balances explanation and prediction? And the results are remarkably consistent with what we found in Journal of the Association for Information Systems. Also, the BIC and the GM, they both perform very well in balancing model fit and prediction. So if you're interested in these articles, well, we are currently getting the proofs, so we're going to share them if we are allowed to, obviously, on ResearchGate. Otherwise, I'm happy to share my author copy with you. Just drop me an email or drop me a message on ResearchGate. I'm happy to do that. We also prepared an Excel template on PLS-SEM.net, which you can find under downloads. And you can use this template to calculate these criteria. So this is what it actually looks like. The only thing that you need to specify is the R-square, the target construct of the saturated model. And you actually don't need that for all of these criteria. The number of immediate predictors for the target construct and the sample size. And this Excel sheet will compute these model selection criteria for you. So I think I'm pretty excited about this. And I hope you are too. So in light of the time, I actually want to show you some of the things in Smart PLS, but I think hopefully I gave you a reasonable good overview of what's happening and how to interpret these things. If you have problems, just drop me an email. We are actually now working on a little tutorial article on PLSpredict, and we're happy to share preliminary versions of the article with you if you like. Just drop me a message and we'll send that to you. And well, keep updated on ResearchGate. So, well, thank you, everyone. And I think hopefully we have still some time for questions, right, Faizan?
Marko, well done. This was very, very interesting. Now, yes, we have time, depending on if you have time. We have quite a few questions on Facebook and on Zoom. So I'll start with Zoom. And again, people who are on Facebook, if you have any questions, you can post them in the comments on Facebook main video page. So Marko, what you can do is if you see on your screen down where there's a share screen button, there would be another button with Q&A.
Ah, yeah, I see that.
Right. So if you click on Q&A, you will see a list of questions which people have posted there. I mean, you can answer them one by one, depending on whichever you want to answer. So.
Okay. Yeah, sure. Let's start with the first one. Vikas Arawal. Okay, how can we use it for prediction? And you're correctly pointing out that many people use. Should I repeat the question? Can everyone see it actually, Faizan, or is it only me?
I think everybody can see the question.
Okay. So the question is, how can we use it for prediction? So the first one. And well, I hopefully I answered that in the course of the presentation. I see the question came in a little earlier. And yeah, we use it for predicting case values of the original data which were taken out in the holdout sample. And they can actually come from the same sample, but they can also come from different samples. Like we use this survey to, well, to get data from different population or from different contexts, yeah, let's say a different culture. And then we use these estimates to predict the stability of our estimates from another context. And well, in PLSpredict, actually use a sub-sample, yeah, a subpart of your sample. So that's how you use it. And it doesn't matter if that actually comes from survey or from some secondary data source. Yeah, it doesn't really matter. So hopefully I answered that. Yeah.
Marko, I just want to stop you here. Sorry. I just realized that Facebook people cannot see the questions since the questions are on Zoom. So if you are not using your slides, I will share my screen. That way everybody can see the questions on the screen.
Okay.
So if you look at the screen now, everybody can see the question. So while you are answering the questions, people on Facebook can also look at the questions on screen. Is that okay?
Okay. Well, why is it non-parametric? Well, because we don't make the assumption of normally distributed errors. There are actually, in the course of the estimation, there are some assumptions regarding the normality. So it's actually not truly non-parametric. That's right, but violations of this are not severe at all. Yeah, it's a bit like in OLS. I mean, yeah, it is parametric, but it's not one of the Gauss-Markov assumptions, right? I mean, if you have non-normally distributed errors, well, worst thing that happens is you can't interpret the t-values anymore. In PLS, we don't go that route in deriving t-values right away. We use bootstrapping to get them. Yeah, so this is what makes non-parametric in this sense. Yeah, regarding linearity and all these things, obviously we have to check for that. Yeah, and actually we also have to check for omitted variable bias endogeneity, and happy to share that with you. Just 3 days ago, our paper on endogeneity assessment and treatment in PLS has been accepted in Journal of International Marketing. We haven't shared that with everyone, but we will. And so this is a way of, well, again, testing one of these issues in OLS that, well, currently deal with in OLS. You know, is it an alternative to CB-SEM? I'm not going to go into detail here because this has really been documented in the literature. I hope you forgive me. We have so many questions. How to run PLS-Predict with smart PLS and R software? I think we have some time. I mean, I have time. I can show you, okay? So maybe I can share my screen with you. Is that okay?
Yes, Marco, I'll stop sharing my screen. You can go ahead and share your screen so that people can see.
Yeah, okay. So I just showed that to you in case. Okay, so here it is in Smart PLS. And this is our model, the one that I showed you before, right? And it's one of the sample models also that comes with the software. So I just go to calculate and PLS-Predict, and there's not much that I need to do here. I just need to specify the number of folds, so the number of runs and like the bins and how many bins the data is going to be specified or partitioned, let's put it like that, and the number of repetitions. And I'm just using the default values, which we would suggest until somebody else comes up with another reasonable number. But 10 folds is typical in prediction studies. The repetitions, well, it's more like how much time you have on your hand. You know? So, and what you see here are the prediction errors for the individual items. So these are the items actually from the endogenous constructs. And let's focus on the customer loyalty ones, because this is the final target construct in the model. So loyalty, COSL 1, 2, and 3, these are actually the target constructs, or the target indicators of our model. And what you see here are the RMSE values, the MAE values, and the MAPE values of the PLS models. And you also get the Qsquare, which is kind of the naive training, like the mean value. Yeah, but let's focus on the RMSE and MAE values. As I told you, the MAPE is not really very handy because of the restriction in terms of the 0 values. And what we do now, we compare the PLS estimates here with the LM estimates. LM is the naive benchmark, and the naive benchmark is the regression of, say, customer loyalty 1 on the exogenous constructs indicators. So by specifying such a linear model, we are neglecting the entire model structure. It's only the input layer, the exogenous constructs, and the output layer, kind of the customer loyalty. And we would expect that these values here are actually larger than the errors produced in PLS, because in PLS you have an entire fancy model that you specified, and you want this model to be better than the naive benchmark. And as you can see here, the RMSE for customer loyalty 1 is 1.301, versus in customer loyalty 1 in the naive benchmark is 1.309. So you have a slight better prediction in the PLS model. For customer loyalty 2, we've got 1.525, in the linear model here, we've got 1.539, so better prediction here. And finally, for customer loyalty 3, 1.532 versus 1.573. So again, we've got a smaller RMSE induced error in the PLS model compared to the linear model, which would support that we actually have predictive power in this model. So this is how we deal with the PLSpredict. Yeah. Should we look into another question? What do you think? Q&A. There we are.
Yes, Marko. So I can read the question quickly so that everybody can hear it. We have some problem with questions on Facebook, like nobody can see them. So the next question was, can we report D_ULS and all those model fit indices for simple PLS models? I'm confused that these measures are suitable only for PLS consistent.
Yeah, the question is where they actually, this notion comes from that they are only suitable for consistent PLS. It's probably because these measures have been advocated in articles which also advocate the use of consistent PLS. Yeah, so there's actually no good reason why it is limited to consistent PLS, but it can also use the regular PLS. Yeah, sure, with all the limitations I talked about. Yeah, so in terms of thresholds, in terms of the actual computation and all that. But I understand now from a publication perspective, this is what reviewers request you and me to do, and you might want to go down that route. Yeah, but I'm not fully convinced that it's always correct. That's all I can say. Yeah.
Thank you.
Is there any relation?
So, Marko, the next question is there any relationship between these criteria and R-square of the construct?
Slightly, I never thought about it. But it could be in the RMS theta. I would expect that there is, yeah, because if you have high residual correlations, that's also going to boil down to the R-square thing. With the SRMR, I'm not sure about that. Rather not, I would say, but I'm not 100% certain. Yeah, with the RMS theta, yes, I think there is. Yeah.
All right, thank you. So the next question is, I'm planning to study the relationships between utilization and implementation of healthcare service. This will involve two groups of population, which are the public and the healthcare professionals. Is it possible to create the path model? Oh.
Yes, you would create one path model and estimate it in two different groups. So in the first group and the second group. And then you would, to do that, you would have to establish measurement invariance first. There's this MECOM procedure, which you might have seen. And MECOM is a procedure for establishing this measurement invariance, and it's also implemented in Smart PLS. And yeah, once you have established at least partial measurement invariance, you can actually compare the path coefficients among these groups using multi-group analysis. There's actually a nice paper or chapter in the edited volume by Latane and Noonan, published last year, on multi-group comparison. And we also have a chapter in there on unobserved heterogeneity, in which we also talk a bit about this thing, especially about the MECOM approach. But in case you have questions, drop me an email and I'll just send you the papers, okay?
Sure. Marko, the questions are increasing, so we'll see. Whenever you are done, like whenever you think we should be done, just let me know. And then for those people whose questions are not answered, we can...
we should just do another seminar, I think. What do you think? Yeah,
yeah. I mean, of course, if you agree, we can do another seminar just for questions and answers related to PLS. You know, we can do that. Because I don't know right now what's the time in Germany, so...
It's 5:20, so I'm still okay. Don't worry. Okay. I'm just not at home at the friend's place, and they're probably going to drop in a second. So let's just go, yeah, until...
Okay, all right. Okay, so thank you for being so kind, Marko. So I'll go with the next question, which is, I have a question about justifying choice of measurement approach for formative versus reflective. Since there's a lot of debate about this concept among methodologists, there are a lot of references there.
Yeah, it's a kind of, yeah, I know. There are two layers here. Yeah, the first one is actually the measurements layer, where we talk about measurement conceptualization. Yeah, so we ask ourselves, okay, how do we actually specify a measurement model? This is independent from the actual estimation layer, and we try to lay this out in a 2016 JBR article where we distinguish these different layers. I don't think there's much debate that you can actually specify something formatively, and I'm just using this term. Know that there's lots of baggage coming with it, but there are actually concepts where you combine several indicators to form them, like the marketing mix, for example, is a nice example that your Kensler always brings up. You have the price policy, and you get the distribution policy and the product policy and so on. So this is actually formed, and we would call that a formative measurement model conceptualization. So this is different from the actual statistical treatment of them. Yeah. As you know, PLS always computes composite models and kind of like treats them as formative, even though it's actually not happening at in the back end. Yeah. But
right.
Yeah, this is it. Yeah.
So thank you, Marko. Now the next question is a very interesting one. We have got a lot of experience with this. So the person is asking, at least one mainstream journal started rejecting any study based on PLS. Why PLS community does not do anything about it?
Oh no, we do. We actually published a rejoinder in organization research methods, in which, where I believe we refuted all these comments, and the critical paper by Rönke and Evermann, I think they did a good job. They just they pointed to some real issues and some areas where we really need to dig into. But it's actually always a good thing if you criticize something also to offer solutions. Yeah, and that's what we did in the organization research method article, and we are still doing it. For example, in this JBR article 2016, and we are working on it. For example, endogeneity. That was also one of the issues raised in organization research methods, and we said, well, that's true. We need to tackle it, so we did. Yeah, so we're working on it personally, and this is fully independent from me working in PLS. I think it's not a very wise approach to desk reject journal articles on the grounds of some method. It's just strange to me, yeah, because there is a place for practically every method in the world, yeah. So there are certainly inferior methods and superior methods in several situations, but if you want, you can let every method fail, including regression, including an ANOVA, including covariance-based SEM, simply because there's like one, or there are 2 or 3 papers, I think, that very, in a very strong rhetoric, criticize PLS, desk rejecting all papers. I just don't think that's a very smart thing to do. Yeah? We should rather work on improving it because the method has merits. Yeah, it offers you means to predict and explain. It offers you to estimate very complex models, and so yeah, we're just not responding directly to these authors anymore. We did this once, twice, yeah, and I think that's it. Yeah, we refuted the comments, and we just don't want to reiterate these things. That's why.
Thank you, Marko. I would also so these questions we were taking were from Zoom. There are a few more, but I would also shift to Facebook. There are a few questions there, and I also want to thank Professor Roldan for answering some of the questions related to PLS consistent on Facebook Live. So just wanted to appreciate that. There's a question which says that redundancy analysis show value less than cutoff value, which is 0.62. This is below the defined thresholds, which shows that my scale is fall short of convergent validity. Please advise what can be done from statistical or procedural point of view to settle or justify the issue.
This is the formative model or the redundancy analysis in. Or which one? Sorry.
Yeah, so that's all we have. So Mumtaz, if you are listening to it, if you can add some more details to your questions, please. So we will wait for some detail on this question. A formative model.
Ah, yeah, okay, got it. Just to clarify, yeah. Well, what can you do? It's a good question. Basically, it's telling us that the formative measurement is not fully capturing the essence of the reflective alternative measurement. So there are two reasons why this is happening. First one, either the reflective measurement is corrupt, or the formative measurement is not strong enough, meaning you don't have enough predictors. So usually the problem with redundancy analysis is that you always have this endogenous construct, which is either measured with a single item or with reflective multi-items. And so there's also always some ambiguity to the quality of the target construct, the endogenous one. But assuming that you did a good job in specifying this, the result would tell us that you actually need more indicators or better indicators for the formative construct. It's obviously bad news because you likely already gathered the data, right? So bad. Sorry. Yeah.
All right. So thank you, Marko. Are you okay if I go ahead, keep going with the questions?
Go ahead.
Okay.
As long as not everyone drops out, that's fine.
So, okay, we have right now 7 open questions, so I'll just go on with them. We have a question says, can we look at the total effect across all latent factors and use that to compute a relative impact of all exogenous variables on one endogenous variable?
Sure, yeah, that's how you do it, yeah, that's true.
Okay.
That's how it's fine. Mm-hmm.
Now, the same person asked another question, which says that how much impact do number of measured variables or items in a latent variable impact the effect of that variable on another variable, which simply means that if I have A and B causing C, A has 10 items, B has 5 items, does this create an unnecessary bias towards A in my model?
Yeah, it tends to do so, yes. That's what we actually took a look at in our studies on single item scaling. And this is now the extreme case, yeah, where you look into a single item where you reduce it to the max, and where the more indicators you have, the lower the error is going to be, because the error averages out if you increase the number of indicators. In CP-SEM, this was never really an issue because most people want to minimize the number of indicators that they use to get the model identified. So you use like 3 or 4 indicators per construct to get it at least identified. So that's why most CP-SEM models have 3 or 4 indicators. Now with PLS, we are suddenly looking at a method which can accommodate several hundred indicators per construct in theory. And this, in fact, triggers a certain bias. Now, I wouldn't really call it severe bias, but it's a slight tendency, let's put it like this, yeah, that some effects are probably inflated a bit, yeah, but it's not going to be severe. Yeah.
Thank you, Marko. So now another question is, I've heard that SEM is overused in hospitality field of study. How does smart PLS differs, which I believe it's covariance-based and PLS-based SEM, and what are the future projections of this being saturated in the near future?
Well, Faizan, I'll probably give that back to you. You're the hospitality man here.
So yeah, I just wanted to say that we did a paper, like me, Marko, Christian, we all did a paper recently on the usage of PLS in hospitality. I think the answer to this question is in that paper, comparing the use of PLS, covariance-based SEM and PLS-SEM. So I would recommend reading that paper. It does explain some of this stuff. All right, and then there's another question, which is, are there any plans to update Smart PLS 3? I think Ringel, Christian Ringel would be the best person to ask.
Yeah, he's in charge of it. Actually, I'm not officially part of the Smart PLS team, yeah. Most people think I am, but we are obviously working on the algorithms together. But yeah, he keeps me updated on the progress. And yeah, sure. There are lots of things happening in the background, like these model comparison indices. The endogeneity is something that they're going to tackle soon. Different types of algorithms. Yeah, there are going to be updates, and pretty soon too. Yeah.
Okay, so Marko, we are left with last 3 questions, and I'm going to go quickly through them. How can we use control variables in SEM? Should we control only dependent variable or all the variables?
Well, yeah, only the dependent variables, because the control variables account for part of the variation in the dependent variable. And what you would do in PLS, let's say you have an endogenous variable like customer loyalty or so, yeah, like in our model, and you want to control for age, you would have a new construct in with a single item, age. And here, single item is not a problem because age is directly observable. And you would link this construct to the customer loyalty construct, to the endogenous one. I'm aware that there's quite a bit of discussion about the choice and the specification of control variables. There's a nice article in Organizational Research Methods on this. And I would just advise you to take a look at that. But yeah, you can do it, and
okay,
to a certain degree you should do it, yeah.
All right, thank you. Now, another question is, can you explain a bit about consistent PLS bootstrapping? I don't know if you have to go to PLS, Smart PLS to do this. If you have to do that, I'll ask the last question before this. So there's another question, which is recently some papers are trying to use a kind of nonlinear method, including PLS-SEM. How is your opinion on using the nonlinear methods?
Yeah, probably first about consistent PLS. I'm not going to go into the software now because it takes a while to run the bootstrapping. Yeah, the bootstrap, like first of all, consistent PLS is, for those that don't know what it really is, yeah, it is alternative PLS algorithm which corrects for the PLS bias. And the PLS bias, I'm using this term cautiously here, because PLS provides biased estimates in case you have purely factor model data, so from a factor model population. If you have composite model data, PLS is unbiased. Yeah? So whether your data come from a common factor model or composite model, difficult to tell. Yeah, and actually that's one of the pending issues now for researchers to find that out. The thing is, PLS-C, to correct these estimates, it uses this reliability coefficient rho A. And the problem with the bootstrapping in PLS-C is, if you randomly draw on observations and then you're computing the rho A. But if you have a very extreme sample, the rho A is also going to be very extreme. And this extremeness has a very negative effect on the correction factor. So the correction is going to be super severe. Yeah. How to deal with this? Adanko, which was the first software to implement PLS-C, to the best of my understanding, what they did, they just took out the extreme bootstraps. So I might be wrong about that. And if I'm sorry, Jörg, yeah, maybe you changed this by now, but they basically deleted the extreme samples, which is kind of twiddling around with the data. So I don't know how they actually resolved it. And to be very frank, I don't know how Smart PLS is doing this at the moment. Yeah. So this is certainly an issue in PLS-C-based bootstrapping. And the final question, the nonlinear. Yeah, nonlinearities are part of everyday life. That's true. And there are many situations where relationships are rather nonlinear than linear. Yeah, that's also one of the key selling points of programs such as Warp PLS, yeah, which try to find out these nonlinearities. So Newsreel, for example, another software which does a good job in identifying them. The thing is, if you have nonlinear relationship, then it gets very difficult to interpret these relationships and these estimates. And standard assessments like the Rsquare suddenly don't work anymore. You need like pseudo Rsquare and so on. In most cases, unless you have like extreme forms like a U-curve or so, in most cases, the linear relationship is a reasonable approximation of a nonlinear relationship in most terms. This is not always true, yeah, but it's true in most cases, because if you look at standard regression models across like all of science, and I'm not talking about social science now, I'm all of science, yeah, you typically don't see researchers pre-specify nonlinear relationships. If they estimate something nonlinear way, they do it like Newsreel, for example, where they have neural networks which try to fit like the lines specifically to the data set. This is truly exploitation then, because you're overfitting the data that you have, and this is not what prediction is all about. When you take prediction seriously, I think it's better to stick with linear relationships as long as they are actually reasonable to defend.
All right. Thank you very much, Marko. I really appreciate the time you have taken. Actually, we have passed the 1 hour pretty early. So
Okay.
yeah, and I'm happy that there's a lot of interest in PLS and people have questions, and then we have amazing people like yourself who are willing to share their knowledge and their expertise with everybody. So we'll probably work on another webinar to see if there are any questions, and if you're willing, I'll probably invite you again. For now, I really appreciate and I thank you. For the people who are online or who are listening throughout, I thank you all to come join this webinar. And one announcement is that this webinar is recorded. So once we are done, we'll be uploading the video on the website of ANAHEI. So you can always go back and watch the whole video, and we can also send an email to all the people who registered with a link to the video. So if you have missed any of the answers to the questions, you can go back and listen to the answers to all the questions that were asked. With that, I think it's time to be done with this webinar. Marko, do you have anything else to say?
Just thank you. Thank you for listening. Thanks for your fantastic questions. Very much enjoyed it. It would be nice to come back and yeah, drop some emails to Faizan and me in case you have specific requests for topics. That'd be nice.
Of course, again, yes. If you have any questions, any concerns or comments, you can email me or Marko, and we'll be happy to answer your questions. Thank you once again. Thank you,
one thing, we are going to be offering a seminar on basics and recent advances in Hamburg in June. So in case you want to join us, come by, or we are always happy to come by your place, obviously. Yeah.
Sure. And the details about that seminar are on Smart PLS's website and on Facebook page. So if you need any details, you can get on the website or Facebook page. Thank you.
Super. Thank you very much.